Yes, so we are in the application of first homomorphism theorem, and in last lecture we had discussed some applications of first homomorphism theorem. So let us continue this discussion with further applications. So I think in last lecture we had discussed 8 applications, and the last result was, I think, R quotient Z is it is isomorphic to unit circle, right? Okay, now next, so let us see one application in the group of permutation, that is Sn. So 9, let H be any subgroup of Sn, then H contains then we write in this way, then H contains all the permutations then either all permutations in H are even or exactly half are even. So this is one result. Okay, so what this result want to say? So let us try to understand first of all this result, then we will prove it. So what we have, H is any subgroup of Sn, and Sn is what? It is a group of permutation. So in H, elements of Sn are coming. So in H, some elements may be even permutations, some elements may be odd permutations, and permutations is either even or odd. So here result says that either all permutation in H are even, मीन्स H में जितने भी परम्यूटेशन है या तो सब इवन परम्यूटेशन है, यदि कोई ऑड परम्यूटेशन भी है, H कंसिस्ट विथ आइदर ऑल इवन परम्यूटेशन, यदि इसमें कोई ऑड परम्यूटेशन आ गया देन एग्जैक्टली हाफ आर इवन. फॉर एग्जांपल, सपोज ऑर्डर ऑफ H इज 20, से ऑर्डर ऑफ H इज 20. So there are two possibility. All these 20 permutations are even. All 20 are even permutations. So this is case 1. And other case, second case is what? If at least one permutation is odd, then it will not be only one. It will be exactly half, that is 10. So second possibility is 10 are even and 10 are odd. ऐसा नहीं होगा कि 5 are even and 15 are odd, और ऐसा भी नहीं होगा कि suppose 8 are even and 12 are odd and total is 20. See, this situation is not possible. या तो सारे इवन परम्यूटेशन है या exactly half are even and exactly half are odd. So only these two situations are possible, right? Okay. So let us try to prove this. So proof is very simple. Let H be a subgroup of Sn. If all permutations are even, then we are done. If all the permutations in H are even, then we are done. All permutations are in H are even. If it contains some odd permutation, then we have to prove that exactly half are odd and exactly half are even. So let H be a subgroup of Sn such that H contains at least one odd permutation. At least one, let me write here, at least one odd permutation. मतलब सब इवन है, देन वी आर डन, बिकॉज ऑल आर इवन एंड इट इज इन द स्टेटमेंट. यदि उसमें कोई ओड आ रहा है, देन वी विल प्रूव दैट odd are exactly half of the total, or even are exactly half of the total. Okay, so now you define f is a mapping from H to this group -1, 1 with respect to usual multiplication, and we know this is a group having two elements with respect to usual multiplication, and identity of this group is +1. And H is this subgroup of Sn. So now you define the function in this way: f of sigma is equal to 1 if sigma is even and -1 if sigma is odd. Already we have discussed this function. It will be a homomorphism, and we had defined this from Sn to here, and it becomes a homomorphism. So by the same argument, you take any two member from H, sigma and mu. If both are even, if both are odd, one odd, one even, even, odd, and you just find out sigma into mu, odd into odd, odd into even, 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 odd, odd, and apply the definition of f, and you can verify. Then let me directly write, then f is a homomorphism. So I am not writing the proof here, already I had discussed in some previous lecture, right? So then f is a homomorphism. Now what is the kernel? Let us see what is kernel. Okay, before going kernel, here H contains at least one odd permutation. So that odd permutation you consider, let us say alpha is that odd permutation. Alpha belongs to H is what? Odd permutation is odd. Then what will be f of alpha? F of alpha will be -1, and H is a subgroup of Sn, so definitely identity is there. So f of that identity, say I, so it is even permutation, so it is 1. So there is some element in H whose image is -1, there is some element in H whose image is +1. So range of f is -1 and 1, -1, 1. So both the element will comes into the range. So in short, my this f is what? It is on to, range is -1 to 1. So is homomorphism, and f of H is what? It is -1, 1. Range will range is -1, 1, because we assume that H contains at least one odd permutation. So the image of that odd permutation will be -1, and identity is already there, so even permutation is also there, so its image will be 1. So range is -1, 1. Now you look at the kernel. So kernel of f is what? It is what? It is sigma belongs to H such that f of sigma is equal to identity element of this group, and that is 1. So it means what? Sigma belongs to H such that f of sigma is 1. It means what? Sigma is even permutation, right? So ये जो कर्नल है वो क्या मिल रही है कि H में से ऐसे परम्यूटेशन जो इवन हो, राइट? कर्नल F is what? The permutation from H which are even. Okay, so kernel of f is this. So therefore what is the order of kernel of f? Kernel of f का order क्या रहेगा? So it is what? It is number of even permutations in H. H में जितने even permutation है, it's total, right? So kernel of f में कितने एलिमेंट आएंगे? जितने H में even permutation है. So order of kernel of f is what? Number of even permutations in H. So that is one thing. Now by first homomorphism theorem, what we have? G quotient kernel of f. Here G is what? H. H quotient kernel of f, it is isomorphic to f of H. It will be isomorphic to f of H. So these two groups are isomorphic, so its order is also same. H quotient kernel of f is equal to order of fh, right? Why? Because my h is finite. It is a subgroup of Sn. Sn is finite, so its subgroup is finite. So h is finite, so its quotient group is finite. Once my group is finite, its quotient group is always finite. So f of h is also, f of h is just containing two elements. So therefore it is order of h divided by order of kernel of f is equal to order of fh. Order of fh is what? It is 2. Order of fh is 2. So therefore order of kernel of f, order of kernel of f is equal to order of h by 2. But what is order of kernel of f? Number of even permutations in h. So therefore number of even permutations in h is equal to order of h by 2. So hence it is proved. See, हमने शुरुआत कहाँ से की थी कि h is a subgroup of Sn and h contains at least one permutation, at least one odd permutation. We don't know how many odd, right? We don't know how many odd, but it contains some odd permutations, right? And what we have proved, तो ये H में कुछ इवन है, कुछ ऑड परम्यूटेशन है. तो H में इवन परम्यूटेशंस कितने हैं? नंबर ऑफ इवन परम्यूटेशन इन H इज व्हाट? ऑर्डर ऑफ H, दैट इज टोटल परम्यूटेशन डिवाइड बाय 2, मीन्स हाफ आर इवन, right? Half are even, so remaining are odd, right? So exactly half are even, and let me add here, and half are odd. तो यदि मेरे H में एटलीस्ट वन ऑड परम्यूटेशन भी आ गया, देन नंबर ऑफ ऑड परम्यूटेशन इन H आर व्हाट? नंबर ऑफ ऑड परम्यूटेशंस आर exactly half of the total number of permutation, and number of even permutation are also exactly half of the total number of permutation. तो मतलब कि सपोज मेरे पास अभी हमने एग्जांपल देखा था, सपोज H इज अ सब ग्रुप ऑफ Sn एंड ऑर्डर ऑफ H इज इक्वल टू से 20 और लेट मी से 30, and if then there are only two possibility. Either all the elements of H are even permutation, means all 30 permutations are even permutation, or if it has some odd permutation, if H contains some odd permutation also, then number of odd permutation in H are 15 and number of even permutation in H are 15. It will not happen that 10 are odd permutations and 10 are even permutations. No, it will not happen. See, so it means what? Let us see one further application of this result. Suppose let H be a subgroup of S5 and order of H is say 15. Order of H is 15. So if you say how many permutation in H are even and how many are odd, so I claim that all the permutations in H are even. Why? Because if it contains at least one odd permutation, then exactly half are even and exactly half are odd. So half of 15 sorry half of 15 is what? 15 by 2, 7.5. So 7.5 are even and 7.5 are odd permutations, so that is not possible, right? 7.5 permutations are even permutation and 7.5 are odd permutation, that is not possible. So if odd, then we do not have its two equal part, right? So this result will not true here, right? But result is true, right? So once we have 15, order of H is 15, that is odd. 15 is what? It is odd. So then it means what? All the permutations in H are must be even. It will not happen some permutations are odd. If some permutations are odd, then exactly half are odd and exactly half are even, and half is 7.5, and that is not possible, right? So in short, here 15 is not important. Important is what this number is odd. So if you have given S5 and suppose it contains some it has some subgroup of odd order, then all the permutations in that H must be even, and as a result 15 is odd, so implies all permutations in H are even. So it means what, H का हर एक मेंबर इवन परम्यूटेशन है, सो H का हर एक मेंबर कहाँ बिलोंग करेगा, AN में, because AN contains all even permutation, so H is also a subgroup of AN. So it means what, odd order subgroup of SN in general, odd order subgroup of SN is also a subgroup of AN, right? So let us write that result here. So it is simple corollary of this result number 9. So let me write in this way, are odd, and the another result, let me say it is 9A, and 9B is what, every odd ordered subgroup of SN is also a subgroup of AN. मतलब कि odd order का कोई भी subgroup दे दिया SN का, then it will be also a subgroup of SN. For example, suppose let me give one, suppose you consider S10, let K is a subgroup of S10 and order of K is say 25, order of K is 25, implies K is also a subgroup of A10. ये A10 का भी subgroup होगा. Why? Because its order is odd. So this is very nice application, and on the base of this result, there is one question was asked in NET exam. We'll discuss that problem also with exactly data, and but the logic is this same one. This what I have given here. That is K is a subgroup of S10 and order of K is 75. So there some, it may be S12 something like that, and order of K is some odd number, but the logic is the same. Order of subgroup of SN is odd, so it must be the subgroup of corresponding AN. Okay, so this is what application number 9. Now let me discuss one concept, then we start the, अभी हम SN की बात कर रहे हैं, then let us discuss one concept, new concept. See, for example, let me start with S3. You consider S3. So S3 consists what? It consists let me write in this way, 1 2 3 1 2 3. Okay, let me write in this way, what identity 1 2 1 3 2 3, then 1 2 3 and 2 1 3. So 1 2 3 4 5 6 elements. So this is my S3, right? Now here I have 3, so I will consider identity matrix of order 3 by 3, and let me say denote it by I also, I. So I is what, it is 1 0 0 0 1 0 0 0 1. Now you consider this one. Now what I will do, now you consider one element from S3. So let sigma belongs to S3. So for example, say sigma is equal to say 2 1 3. So it means what, 1 2 3, 1 goes to 3, 2 goes to 1, and 3 goes to 2. So it is this one. So it means what? Sigma 1 is what? It is 3. Sigma 2 is 1, and sigma 3 is 2, right? Now I consider I sigma. So corresponding to sigma belongs to S3. Sigma here, for example, I have considered 213. Then sigma may be this one, maybe this one, maybe this one, anyone. But here to understand, I consider sigma is 213. Now I sigma. So what is I sigma? So I sigma is what? I sigma is what? It is the matrix. Is the matrix whose it is the n cross n, 3 cross 3. If we are talking about S3, so it is the 3 by 3 matrix whose ith column is, that is first column, second column, third column, is what? Sigma ith column of identity matrix, that is I3, or you say I. So let me produce this sigma, and this matrix is called, I sigma is called permutation matrix. Permutation matrix corresponding to सिग्मा. ये जो सिग्मा है उसकी हेल्प से जो एक मैट्रिक्स बन रहा है, दैट इज कॉल्ड permutation matrix corresponding to sigma. And what do you mean by permutation matrix corresponding to sigma? It means this one. It means this one. So let us try to see how this I sigma looks. So here I sigma is first of all what? It is a 3 by 3 matrix. It is a 3 by 3 matrix whose ith column is sigma ith column of I3. Ith column means first column. So this is first column. First column, here will be second column, and here will be third column. So first column is what? First column is sigma 1th column of identity. Second column is what? Let me write in this way. Second column is what? Sigma 2th column of identity matrix. And third column is what? It is sigma 3rd column of identity matrix. Now sigma 1 is what? Sigma 1 is 3. Sigma 1 is 3. Sigma 2 is what? Sigma 2 is 1. And sigma 3 is what? Sigma 3 is 2. Right? So here first column is what? It is a third column of identity matrix. And third column of identity matrix is what? It is 0 0 1, 0 0 1. Second column is what? It is a first column of identity matrix, and that is what? 1 0 0. So it is 1 0 0. And third column is what? It is the second column of identity matrix, that is 0 1 0. So it is 0 1 0. So in short, my I sigma is what? 0 0 1 1 0 0 0 1 0. So this is my I sigma. So if you look at directly from I to here I sigma, it is not 6, it is sigma. Here directly here, then it is what? It is just some permutation, or it is just permutation of columns of identity matrix, but in some particular manner. And that manner is what? That pattern is what? You consider first column is what? First column is what? That is the where 1 maps 3. So you consider here third column of identity matrix. So if you want to write this matrix directly, right, then what? You just consider 1 maps to where 3. So you consider first column is third column of identity matrix. Then what is second column? So 2 maps to 1. So it is first column. And what is the third column? So 3 maps to where? 3 maps to 2. So third column is second column. So in this way you can obtain I sigma. So let me consider the another one. Say mu is equal to 1 3. So 1 3 means what? 1 2 3, 1 goes to 3, 3 goes to 1, and 2 goes to 2, right? So what will be I mu? Let us write directly. So I mu is what? I want to write first column. So for 1 maps to 3, so you just write third column of the identity matrix, that is 0 0 1. Now I want to write second column. So what is second? 2. So 2 maps to 2, so that is just the second column, so that is 0 1 0. And third column, so third column is 3 maps to 1, so first column, that is 1 0 0. So this is your I mu, right? So these matrices are called permutation matrices, right? Okay, now one more interesting thing, order of sigma. We know what is order of sigma. ये जो sigma है, sigma is what? It is a 2 1 3. It is a 3 cycle, so its order will be 3. Here mu is 1 3, so it is a 2 cycle, so its order is 2. And in general, if you consider say S10 and you consider any sigma, then order of sigma, we know how to find order of sigma. You just express as a product of disjoint cycle, and then it is just a LCM of length of that disjoint cycle. So what is the another interesting thing about this I sigma and sigma? So order of this I sigma will be same as order of sigma. So order of permutation matrix is same as the order of the permutation. So that is one interesting result. तो इस पर भी एक क्वेश्चन पूछा हुआ है, विल डिस्कस, बट द फैक्ट इज दिस वन, राइट? ऑर्डर ऑफ परम्यूटेशन मैट्रिक्स इज सेम एज ऑर्डर ऑफ परम्यूटेशन. तो वहाँ पे क्वेश्चन कुछ ऐसे फ्रेम किया था, नेट का क्वेश्चन था कि लेट आई सपोज I5 या I4, इट इज समथिंग गिवन, is the identity matrix of order 4 or 5 something, and let sigma be the permutation from S4, and the matrix A is the matrix obtained by considering the ith column of matrix A is the sigma ith column of the matrix of the identity matrix I4. Then what is the order of A? So ultimately that A is what? It is the permutation matrix corresponding to sigma. So instead of finding out that order of A, so order of A is say 4 by 4 or 5 by 5 matrix, I don't remember that 4 by 4 or 5 by 5, but to find out the order of that matrix we need to multiply that how many times? Whatever its order, right? Then you can find out its order. But the better way is what? If you use this result, then order of that matrix is what? Order of the corresponding permutation, and permutation is already given, so it is just matter to find out the order of that permutation, right? So that is the logic. But I want to, I am discussing here this thing for some other purpose. So second thing, see, determinant of I3 is what? Determinant of so let me write down the some properties of permutation matrix. So I hope you know what is permutation matrix. So first property, let sigma belongs to Sn and I sigma be the corresponding, be the permutation matrix corresponding to sigma, then order of I sigma is same as order of sigma. First property. Second thing, determinant of I sigma is non-zero. determinant of I sigma is non-zero for all sigma belongs to Sn. इसका जो डिटरमिनेंट आपको मिलेगा इट विल बी नॉन जीरो. वाई? बिकॉज डिटरमिनेंट ऑफ आई इज व्हाट? Identity matrix of order n by n or whatever you are discussing here. So its determinant is 1, it is non-zero. Now you are just interchanging the columns. You are interchanging the columns, right? So by interchanging the columns, determine the value of the determinant will just change by minus sign. So if you change two columns, then determinant will becomes -1. If you again change two columns, then again becomes minus, so it is negative negative plus 1. So its determinant will be either 1 or -1. So ultimately it is non-zero. So what we have here, all this I sigma for all sigma belongs to Sn, for all sigma belongs to Sn, this I sigma, determinant of I sigma will be either 1 or -1. So determinant of I sigma will be not 0, and as a result I sigma belongs to GL. Suppose I am working with n by n matrices. Here in example we have 3 by 3. So in general n by n, here Sn, so we deal with identity matrix of order n, so it will be the element of n R. So for every I sigma, for every sigma belongs to Sn, I sigma will be the element of GL NR, right? So non-zero for all sigma belongs to Sn, and so let me write third one, I sigma belongs to GL NR for all sigma belongs to Sn. Third thing. Now you consider a set, and that is what, let me give the notation. Say consider H. So H is equal to, you consider I sigma where sigma belongs to Sn. I sigma is what? For fix, okay fine, you consider Sn, then you consider different permutations, and corresponding to that permutation you consider permutation matrices, and you collect all permutation matrices. Then corresponding to when sigma is what? Sigma is equal to identity permutation, right? So this my I sigma is what? In that case I sigma is what? It is identity matrix, right? So identity matrix is also here. So the H, the set of all permutation matrices, it will be a subgroup of GLNR. वो GLNR का subgroup होगा, right? And you can prove this also. It is a product. So proof is very simple. Ultimately this is what? This is a finite group, a finite subset of because Sn is finite, so corresponding to every sigma you have one matrix. So ultimately this collection is finite, first of all. So now you consider any two, I sigma and I mu. You consider I sigma and I mu. So I sigma is what? It is a matrix corresponding to sigma, and I mu is what? It is a matrix corresponding to mu. So its product will be what? It will be I sigma mu. You can verify, right? So I sigma mu, so again sigma mu is what? Sigma and mu belongs to Sn, so sigma mu will be also in Sn, and say it is lambda. So or doesn't matter to say, no need to say it is lambda. So this I sigma mu will be where? It will be H, in H. So it is a finite subset of this GLNR, and it is closed under product, so it is a subgroup, right? It is a closed under operation, not subgroup. It is a closed under matrix multiplication, so it is subgroup. Okay, so this much information we have about the permutation matrix. So in short, if you have given Sn, then corresponding to Sn, we have a subgroup H of GLNR. So my aim is what? What is my aim? So every Sn, this Sn and this H will be what? They will be isomorphic. Why? Sn में कितने elements हैं? n factorial. So corresponding to every permutation you have one matrix. So this cardinality of H is also n factorial. So this is a subgroup of GLNR, and Sn is already a group. So H is also a group, right? So these two group will be isomorphic, right? So I want to state this result. So it means what? For every n, Sn is isomorphic to a subgroup of GLNR. For every n, Sn is isomorphic to a subgroup of GLNR, right? So this is what? This is the statement. So to discuss this statement, I discussed all these things, the concept of permutation matrix, and in between we get these two things. The order of permutation matrix is same as the order of the permutation corresponding to that matrix, right? So let me state finally the result, और let me add one more thing here. तो यहाँ पर हमने क्या प्रूव किया? For every n, Sn is isomorphic to some subgroup of GLNR, and by Cayley's theorem says what? Every group is isomorphic to a group of permutation, right? So if I consider just a finite group, if I consider some finite group, then every finite group is isomorphic to a group of permutation, and when my group is finite, then I say that group of permutation I denote it by Sn. So every group is isomorphic to subgroup of Sn. Every group is, you consider say K is any finite group. K is any finite group. So by Cayley's theorem, what we have? This K will be isomorphic to some subgroup of K will be isomorphic to some subgroup of Sn, group of permutation, because K is finite, so I am considering the group of permutation on a finite set. So K is isomorphic to some subgroup of Sn, and let me say the subgroup of Sn is say L. So K will be isomorphic to L, and L will be some subgroup of Sn. Now from here what we have proved? Sn is isomorphic to H, and H is what? H is some subgroup of GLNR. So we have this link. So what we can conclude from this one and this one? Any finite group K is isomorphic to L, and L is a subgroup of Sn, and this Sn is isomorphic to H. So L is isomorphic to H, and H is what? H is a subgroup of SLNR. So K is isomorphic to H, and it is a subgroup of GLNR. So from here we can also conclude that any finite group is isomorphic to some subgroup of GLNR, right? Any finite group is isomorphic to some subgroup of GLNR. So I have two things. For every n belongs to n, Sn is isomorphic to some subgroup of GLNR, and hence with the help of Cayley's theorem, every finite group is isomorphic to some subgroup of GLNR. So let me quote this result. So this will be the result number 10. for every n, Sn is isomorphic to some subgroup. Sn is isomorphic to a subgroup of, for every n Sn is isomorphic to a subgroup of GLNR, and hence every finite group is isomorphic to a subgroup of GLNR. So this is very important result, and so many times it was asked question based on this statement only. स्टेटमेंट कुछ ऐसे फ्रेम करके दे दिया होगा कि ऐसा कोई ग्रुप है, वो इसके सब ग्रुप को आइसोमॉर्फिक है कि नहीं, येस और नो. सो यू जस्ट अप्लाई दिस रिजल्ट and you will get the answer, and we will discuss problem based on this statement. Okay. Now let us continue some discussion on this GLNR and SLNR. This GLNR and SLNR are very interesting groups. So this is result number 10. So again, this is just by application of first homomorphism theorem, or you may say it is just based on isomorphism. Why it is application of first homomorphism theorem? Because here we have applied the Calais theorem, right? Sorry, I think it is not by the first homomorphism theorem. It is just application of Calais theorem. But anyway, we have some nice result. Okay. Now see, you consider a matrix, say A. A is a matrix, see, cos theta minus sin theta, sin theta, cos theta. You look at this matrix, then what will be A square? So let us see what is A square. First of all, here I can say what is the determinant of A. It is cos square theta plus sin square theta. It is 1, so it is non-zero. So this A will be what? A will be the element of GL2R. You can say it is element of GL2R because its determinant is non-zero, but at the same time it is 1 also. So you can say it is an element of SL2R. It is an element of SL2R. So it is element of SL2R as well as GL2R, but right now I am considering it is an element of SL2R. Now what is A square? Let us see. So A square will be what? It is cos theta minus sin theta, cos theta into cos theta minus sin theta, cos theta, and you just find out its product. Then it is cos into cos square theta minus sin square theta, then here cos into minus sin and minus sin into cos. So both contain minus sign, so let me take minus sign outside, and it is cos into sin, cos theta into sin theta, or plus sin theta into cos theta, right? So it is in fact okay, fine. Now here sin theta, cos theta, sin theta. So it is sin theta into cos theta and cos theta into sin theta. So it is 2 times sin theta into cos theta. Similarly here minus 2 times sin theta cos theta. Let me write in short. And similarly the last entry will be sin into sine, that is minus sine square theta and plus cos square theta. So it is cos square theta minus sine square theta. So this will be what? Cos square theta minus sine square theta is cos 2 theta, minus 2 sine theta cos theta is minus sine 2 theta, and this will be sine 2 theta plus, and this is cos 2 theta, right? So a square will be this. So what do you think, what will be a cube? So by induction you can prove a square is this, so a cube will be cos 3 theta minus sine 3 theta, sine 3 theta and cos 3 theta. So in general, by induction you can prove a to the power n will be cos n theta minus sine n theta, sine n theta and cos n theta. So you remember this thing. If your matrix A is this, then a raised to n is just you multiply n with the angle. See, in general result is this one. See, if you consider this matrix, say A is equal to cos alpha minus sine alpha, I am using just alpha instead of theta here, sine alpha and cos alpha, and this is your say A say alpha, here I am using the angle alpha, so it is say A alpha, let me write in this way, A alpha, and you consider A beta. A beta is what? It is cos beta minus sine beta and cos beta. Then what will be A alpha into A beta? So it is this into this. So it will be this one, cos alpha plus beta minus sine alpha plus beta, sine alpha plus beta and cos alpha plus beta. You can verify, you just multiply by usual matrix multiplication, and you use the formula of cos alpha plus beta and sine alpha plus beta, and you will get this. So it is in notation, it is what? It is just A alpha plus beta. A alpha into A beta is A alpha plus beta. So here what I have? A square. A square means what? It is A theta into A theta. This A is what? Actually in this notation it is A theta. So A square is what? A square is what? It is A theta into A theta. So it will be A theta plus theta, that is A2 theta, and A2 theta is this one. Where it is? Yes, A2 theta is this one. So in general, A raised to n is what? A theta n times, so A n theta, and A n theta is this one, right? So this is just matrix algebra. So in short, if I summarize all this discussion, then determinant of A is 1, which is non-zero, so it will be the element of SL2R. And in general, let me remove all this thing. A raised to n is what? It is cos n theta, negative sine n theta, sine n theta and cos n theta. So this is one thing, right? Okay. Fine. Now suppose you take theta. Let theta is equal to 2 pi by 5. You take theta is equal to 2 pi by 5. तो ये मैट्रिक्स क्या बनेगा? This A will be what? Cos 2 pi by 5, negative sine 2 pi by 5, sine 2 pi by 5 and cos 2 pi by 5. So again its determinant is all 1, and so it will be a member of SL2R. But what happened? If you consider A square, then what you have? You just consider A square, then it is 2 theta. So 2 theta, that is 2 into 2 pi by 5, that is 4 pi by 5. Then A cube will be 3 into 2 pi by 5, that is 6 pi by 5. So cos 4 pi by 5 minus sine 5 pi by 5, minus sine 4 pi by 5, sine 4 pi by 5 and cos 4 pi by 5. So it is not identity matrix, because cos 4 pi by 5 is not 1. Cos theta is equal to 1 implies if and only if theta is equal to 2n pi, वो 2 pi का मल्टीपल होना चाहिए, right? And this is not a multiple of 2 pi. But similarly, a cube, then it will also not identity. A raised to 4, then it is also not identity. Why? See, because if you consider 3, then this angle will be what? It is 3 times 2 pi by 5. It is not multiple of 2 pi. Then and only then it will becomes 1, right? And for identity matrix I need 1 0 0 1. So you forget about remaining 3 entry, you just concentrate on this one, then it will not be the multiple of 2 pi. If you consider a raised to 4, then it is 4 times 2 pi by 5. So again it is not a multiple of 2 pi. But when you consider 5, when you consider a raised to 5, then it will be 5 times 2 pi by 5. 5 cancel and it is 2 pi. So it is what? Cos 2 pi, that is 1. Sin 2 pi, that is 0. Sin 2 pi 0 and cos 2 pi 1. So it is identity. So it means what? A is not identity, a square not identity, a cube not identity, a 4 not identity, a raised to 5 is not identity, a raised to 5 is identity. It means order of A is equal to what? 5. So this is very nice technique to find out element of order 5 in SL2R, right? तो हमने क्या किया? You consider matrix A in this way, and here I have considered theta is 2 pi by n. What happened if I consider theta is equal to 2 pi by 7 in A, theta is 2 pi by 7, then I get order of A is 7. So in general, if theta is equal to 2 pi by n, theta is equal to 2 pi by n, where n is any positive integer, then order of A is n. So this is a technique to find out element of order n in SL2R. It is technique to find out element of order n in SL2R, right? So let me summarize this thing. So you consider A equal to this, then it is a member of SL2R, its determinant is 1, then A raised to n is this one, right? So next, if theta is equal to let n belongs to n and theta is equal to 2 pi by n, and you consider A is equal to this cos theta negative sin theta and cos theta, then order of A is equal to n. तो इसका मतलब क्या हुआ कि in Sn for given any n there is an element of order n order का element आपको मिलेगा ही मिलेगा, right? So it means what? For given n belongs to n, SL2R has an element of order n. मतलब कि कोई भी पॉजिटिव इंटीजर n के लिए SL2R में n ऑर्डर का एलिमेंट अवेलेबल है, एंड दिस इज वे टू कंस्ट्रक्ट दैट एलिमेंट. ओके, so now what I will do, let me remove this. Okay, let me remove this also. So let n is equal to let 8 belongs to n. Now what I will consider, you consider theta is equal to 2 pi by 8. So it is what? It will be pi by 4, and you consider A is equal to cos pi by 4 minus sin pi by 4, sin pi by 4 and cos pi by 4. So this is will be element of SL2R. Now order of A will be what? It will be 8. So it is pi by 4, but its order will be 8, right? So order of A is 8. Now you consider H is equal to group generated by A. So see, A is in SLNR, so A square, A cube, A raised to 4 up to A raised to 7 all will be element of SL2R. So it will be what? Identity, that is A raised to 0, A square, A cube up to and so on A raised to 7. So this will be, and here this is what? This is what? This H is what? It is a subgroup of SL2R. It is a subgroup of SL2R, right? And this is what? Any cyclic group. So now this is what? This is a cyclic group of order 8 and it is in SL2R. So every finite cyclic group, now if you consider any finite cyclic group, then it is isomorphic to Zn. So this H will be also what? It will be also isomorphic to Z8. So it means what? And so Z8, it is isomorphic to H, and H is a subgroup of SL2R. Now any cyclic group of order 8. Now you consider any cyclic group of order 8. Let me say say K is a cyclic group of order 8, then it will be isomorphic to Z8, and Z8 is isomorphic to H, and H is a subgroup of SL2R. So what does it mean? If K is any cyclic group of order 8, then it is isomorphic to H, because K is isomorphic to Z8, Z8 is isomorphic to H, and H is a subgroup of SL2R. So it means any cyclic group of order 8 is isomorphic to some subgroup of SL2R. So here 8 is not special. For any n belongs to n. So any finite cyclic group is isomorphic to a subgroup of SL2R. Right? So this is a statement. This is one line conclusion of this whole discussion, that any finite cyclic group is isomorphic to some subgroup of SL2R. मतलब कोई भी आपको साइक्लिक ग्रुप दिया है फाइनाइट ऑर्डर का, तो उनके जैसा एक सबग्रुप SLR में बैठा है. SL2R contains a cyclic group of every order, every finite order. Infinite order का भी है. You consider say if you consider one more observation, you consider this matrix A, and you consider theta is equal to 2 pi by root 2. You consider theta is equal to 2 pi by root 2. तो ये थीटा क्या हो गया? root 2 pi. Now you consider power of A, right? Then you will never get, you consider power of A, then here you have A raised to n is what? Cos n theta. तो ये अब n से मल्टीप्लाई करेंगे, n theta, then it is what? n into root 2 pi. तो कौन से n के लिए ये 2 pi का मल्टीपल हो जाएगा? No such n exist, right? Because root 2 is irrational number. So you will never get identity matrix, right? So you consider that matrix A is equal to cos theta minus sin theta cos theta, and theta is root 2 pi. Then you consider A square, A cube, and so on, right? You consider this sequence of powers of A, then it will never becomes an identity matrix, right? So you have one element of infinite order in SL2R, not one element. You have uncountably many elements. You consider any irrational number, and irrational numbers are uncountable. So there are uncountable matrices, uncountable many elements in SL2R whose order is infinite. So with the help of that matrix, you consider a subgroup. सो इट विल बी व्हाट, इट विल बी इनफाइनाइट साइक्लिक सब ग्रुप। तो मतलब कि Sl2r में एक इनफाइनाइट साइक्लिक ग्रुप भी कंटेन हुआ मिलेगा आपको। सो दैट इज Sl2r कंटेन्स एन इनफाइनाइट साइक्लिक सब ग्रुप एज वेल एज Sl2r कंटेन्स every finite cyclic subgroup also. So in short, all this discussion can be put in one line in this way. So let us conclude all this discussion in terms of statement. So 11, every finite cyclic group is isomorphic to a subgroup of Sl2r, and every infinite cyclic group is isomorphic to a subgroup of Sl2r. See, Sl2r के कोई सबग्रुप के साथ आइसोमॉर्फिक होना है किसी इनफाइनाइट साइक्लिक ग्रुप को, इट मीन्स व्हाट, we need at least one element in Sl2r whose order is infinite, then we are done. Why? Because with the help of that element you just generate the subgroup of Sl2r and it will be infinite cyclic group, and we know how to find out infinite order element in Sl2r. You just take theta is equal to 2 pi by some irrational number, and you consider theta equal to 2 pi by some positive integer, and then this A will have finite order of that order n. Okay, so this is what one interesting result. Now next result. Okay, so let me continue the discussion with the element of this Sl2r. See, you consider A is equal to this cos theta minus sin theta and cos theta. So it is element of Sl2r. Now order of and you consider where theta is equal to 2 pi by n. For n belongs to n, theta is 2 pi by n. तो क्या होगा, then this order of A will be n. So this is first thing. Now second thing, you consider B is equal to 0 1 1 0. So okay, this is an element of Sl2r, but I can say it is element of Gl2r also. Let me consider now it is an element of Gl2r. Now you consider B equal to this, then determinant of B is what? It is 0 minus 1. Determinant of B is what? It is negative 1. So it is an element of Gl2r. Why I have changed here G instead of S? Because this element is of Gl2r, not of Sl2r, because its determinant is minus 1, negative 1. That's I have here changed, because I want both the element in the same group. Okay, so determinant of B is minus 1, so it will be the element of Gl2r. Now let us see what is the order of B. So B is not identity. So let me see what is B square. So it is 0 1 1 0 into 0 1 1 0. So it will be what? 0 1 1 0 0 0 0 and 1 0. So it is identity. So order of B is what? 2. तो क्या हुआ मेरे पास? I have one element A in Gl2r whose order is n, and I have one element in Gl2r whose order is 2. तो Gl2r में एक मेरे पास n ऑर्डर का एलिमेंट है, एक 2 ऑर्डर का एलिमेंट है, राइट? वन थिंग, वो जो n ऑर्डर का एलिमेंट है, n इज ऑन माई हैंड, right? You consider n equal to 3, then I have one element of order 3 and I have one element of order 2. If n is equal to 7, then I have one element of order 7 and one element of order 2, right? Okay, now what is the relation between A and B? A and B I think will not commute. AB is not equal to BA. You can verify. AB is not equal to BA. You just verify. So that this thing, AB is not equal to BA. Okay. But I claim that this AB, order of A is n and order of B is 2, but AB will be is equal to BA inverse. You can verify. AB will be equal to BA inverse. So let us check just now. So AB will be what? What is A? Cos theta minus sin theta, cos theta, and B is 0, 1, 1, 0, and its product will be, this is 0 and it is minus sin theta, 1, 0, so it is cos theta, 0, 1, it is cos theta, sin theta into 0. So this is what product of AB. Now BA inverse. So B is what? 0, 1, 1, 0, and A inverse. What is A inverse? Determinant of A will be 1. So to find out inverse, you just interchange the diagonal element, that is cos theta, you just interchange. Then we have cos theta, and you interchange the sign of the secondary diagonal, that is this minus and this plus. So it is minus sin theta and this will be plus sin theta. So now you just find out. So this will be A inverse. Now multiplication 0 minus sin theta, then 0 cos theta 0, and sin theta 0. So you can see these two matrices are equal. So AB equal to BA inverse, right? So it is just verification. So by similar way you can verify AB and BA will be not equal. You just calculate it, right? Okay, so let me remove this. This is just a calculation. Now what I have in GL2R, I have one element of order n, namely A, one element of order B, one element of order 2, namely B. They are not commuting, but they have relation like AB equal to BA inverse, right? So now this is one discussion. Now you just recall Dn. What is Dn? What is Dn? तो Dn में क्या था? Dn is what? Dn is x raised to I, y raised to j. Dihedral group. X square is identity, y raised to n is identity. I varies from 0, 1 and j varies from 0, 1, 2 up to n minus 1. That is order of x is 2 and order of y is n. And the relation between x and y is what? Yx is equal to xy inverse. तो ये मुझे मिला था dn. तो dn कैसे बना? With the help of two elements x and y. x is of order 2 and y is of order n. ये x का ऑर्डर था 2, y का ऑर्डर था n, और x और y दोनों कम्यूट नहीं कर रहे थे, लेकिन they have relation like this, yx is equal to xy inverse. So if you consider any element of order 2 in any group, you consider one element of order 2, second element of order n, and if x and y have this relation, then you just consider x raised to I and y raised to j, and you collect this type of element, then it will gives you a group like Dn. right? So here what I have in Gl2r, I have one element of order n. So let me consider here what is n order element in Gl2r. It is what? A. So this is my A. One element of order 2, and that is what? B, right? So if you consider this set A raised to B raised to I, A raised to J, where here B square is identity, A raised to N is identity, I varies from 0 1 and J varies from 0 1 to up to N minus 1, and we have already proved that between A and B what we have the relation AB is equal to BA inverse. So this is what? This is your Dn. And here A and B are elements of what? Gl2r. So its power, all the powers of A and all the powers of B are again element of Gl2r, because Gl2r is a group. Now all powers of A and all powers of B are elements of Gl2r. So its product is also elements of Gl2r. So all these elements are of what? Gl2r. So this is what? This is a subgroup of Gl2r. तो क्या प्रूव हुआ? This Dn is a subgroup of Gl2r. और ये n कहाँ से आया था? N is coming from here. For any n belongs to n. So for given any n, Dn, there is a subgroup of Gl2r. ये जो subgroup है, if I say this is my, say, let me say it is say H, then H is a subgroup of Gl2r, but this H is what? It is exactly Dn. So it is H is what? Isomorphic to Dn. In fact, it is Dn, right? So for every n in n, Gl2r has a subgroup like Dn. So Dn is isomorphic to a subgroup of Gl2r. So for every n belongs to n, Dn is isomorphic to a subgroup of Gl2r. So that is a one line of all this discussion. मतलब Gl2r में for given any n you have a subgroup like Dn. In Sl2r for any n you have a finite cyclic subgroup. और Sl2r में है तो वो Gl2r में है ही, because Sl2r is a subgroup of Gl2r. So in Gl2r for given any n you have a finite cyclic subgroup, you have infinite cyclic subgroup. For given any n you have a subgroup like Dn is also there. So GLNR और GLNR में वो अभी हमने जो GLNR डिस्कस किया था, this is Gl2r, right? You can prove it is this true is for NR also. तो उसके लिए आपको मैट्रिक्स थोड़ा चेंज करना पड़ेगा. You just consider this matrix and the remaining entries are 0 0 and 1. So in that case you can also modify, but right now I'm keeping this only up to 2r. तो ये जो GLNR है, GLNR में SN जैसा भी सब ग्रुप है, राइट? DN जैसा भी है, साइक्लिक है, फाइनाइट साइक्लिक, इनफाइनाइट साइक्लिक, और हर टाइप का सब ग्रुप है उसमें GLNR में. सो लेट अस quote दिस थिंग. So result number 12. For every n belongs to n, Dn is isomorphic to a subgroup of Gl2r. So mind this, here I have Gl2r and in previous result I have Sl2r. तो तो यहाँ आप Gl2r कह सकते हैं. Why? Because Sl2r is a subgroup of Gl2r, but here you can't say Sl2r because Gl2r is larger and Sl2r is smaller. Sl2r is sitting inside this. तो आपको इसमें मिल रहा है. It does not means you are finding you can find in Sl2r, but if you find in Sl2r then definitely you will find in Gl2r. So this is the difference between these two, right? मतलब ये साइक्लिक है वो आपको छोटे में भी मिल जाएगा, लेकिन फॉर दिस नॉन साइक्लिक इनफैक्ट इट इज़ नॉन अबेलियन DN. सो नॉन अबेलियन के लिए आपको साइज बड़ी चाहिए टू फाइंड आउट सब ग्रुप लाइक DN इन ग्रुप ऑफ मैट्रिसेस, नॉन सिंगुलर मैट्रिसेस. फाइन. सो दिस इज व्हाट some applications of Calais theorem, homomorphism, isomorphism, first homomorphism theorem. So now we can say now we are doing algebra, right? Otherwise before 3 or 4 lectures we are just doing some calculations. That is not algebra. We can say okay, that is algebra, but this is what actual some interesting facts, how we can analyze group, उसमें क्या है, कौन किस किस के जैसे ग्रुप है. तो वो सब कुछ फाइंड करने के लिए हमें चाहिए होमोमॉर्फिज्म. एंड जब से ये होमोमॉर्फिज्म स्टार्ट हुआ देन वी कैन एनालाइज ग्रुप इन डिटेल, राइट? सो आई थिंक let us just discuss some cardinality, topic on cardinality. So you see, if you see, then in this lecture we our discussion is around GLNR and SLNR. It may be GL2R, SL2R, like that. So we are in GLNR and SLNR. So let us discuss one more point about GLNR and SLNR. See, let me when we learn the ring theory, then we learn field, right? So see, R is a field. When we have field, then we have two operations, usual addition and multiplication. Q is a field, C is a field. So these are some examples of infinite field. So what about the finite field? We know Zn is a group with respect to addition modulo n. And when we learn the ring theory, then we will show that Zn with usual addition and usual not usual addition modulo n and multiplication modulo n, this will forms a ring. And and if n is prime, then there is Zp. Let me say p equal to n and it is prime. So Zp with addition modulo p and multiplication modulo p, this will be a field. So I am not going into the much detail, but this will be a field, right? And order of this Zp is what? It is p. And Zp में कौन से एलिमेंट आएंगे? 0, 1, 2 up to p minus 1. If p is not prime, then it will not be a field. So that is one observation, and I think you also learned in the BSc or MSc course. So these are infinite field and this is one example of a finite field. तो finite field में कितने एलिमेंट हो सकते हैं? What should be the cardinality of a finite field? So there is one result. That result I will not prove, but you just keep in mind. In any field, the cardinality of any finite field is never product of two distinct prime. वो दो अलग अलग प्राइम का प्रोडक्ट नहीं हो सकती. कोई फाइनाइट फील्ड का ऑर्डर 12 नहीं हो सकता, कोई फाइनाइट फील्ड का ऑर्डर 6 नहीं हो सकता, राइट? सो what should be the cardinal? Let F be a, so this is the result, you just write down result. Let F be a finite field, then cardinality of F is equal to P to the power n for some prime P and for some n belongs to n. वो प्राइम का पावर ही हो सकती है. फाइनाइट फील्ड की कार्डिनलिटी must be power of a single prime. It cannot be product of two distinct prime, right? And there is one more result. For given P, for given prime P and for given n belongs to n, there is unique field of order p raised to n up to isomorphism, right? मतलब आपको p की वैल्यू दे दी, फॉर एग्जाम्पल p इक्वल टू 3 एंड से n इज इक्वल टू 4, सो p रेस टू n दैट इज 3 रेस टू 4, इट इज 81. तो आपको 81 ऑर्डर का एक फील्ड मिलेगा एंड इट इज यूनिक. देयर इज ओनली वन फील्ड ऑफ ऑर्डर 81. वो कैसे मिलेंगे वो हम रिंग थियरी में देखेंगे. यू हैव टू कंसिडर वन पॉलिनोमियल of order one polynomial of degree 4, irreducible polynomial of degree 4 over Z3, and with the help of that you can find a field of order 81. We will discuss it later on, but I just tell you the result, you just keep in mind. Yeah, you will get exactly one field of order 81. So let me say F is a field of order, F is a field and order of F is what? It is 81. And suppose you have another field, say K, and K is a field and order of K is also 81, then you can claim that F will be the isomorphic to K. मतलब ये F में जो एलिमेंट है, सपोज F में मेरे पास पॉलिनोमियल है और K में सपोज आई हैव सम मैट्रिसेस, राइट, देन उसका जो फॉर्म है वो डिफरेंट है बट दे आर एल्जेब्रिकली सेम, राइट. सो F विल बी आइसोमॉर्फिक टू K. वो दोनों सेम ही है, सिर्फ उसके जो एलिमेंट्स का फॉर्मेट है, उसके नोटेशन है, दे आर जस्ट डिफरेंट बट दे आर सेम एल्जेब्रिकली. सो दैट इज इन आइसोमॉर्फिक सेंस, राइट. सो लेट मी राइट दिस फैक्ट ऑल्सो हियर. सो second thing, for given n belongs to n and given prime p belongs to n, there exists unique field f of order p raised to n up to isomorphism. So that is the second thing. Okay, so if I see, if I consider here n equal to 1 and p is any prime, then order of field is what? Order of f is p. तो p order का field कौन सा है? And it is immediately, it is ZP. So if you consider any field of order p, then it must be isomorphic to ZP. जब हम ZP को ZP is a group also, ZP with addition modulo p is a group, but when we talk about as a field, then there is one more operation, that is multiplication modulo p also, right? But this is the only field of order p up to isomorphism, right? Okay. So why I am discussing this? See, when we discuss this GLNQ, GLNR, GLNC, so here we are considering the field and these are infinite field, but here you can consider GLNF also, where F is a finite field and let me denote this field with p element by fp. Fp denotes the field having p elements, field having cardinality p. So GL and F, where in general what can I write? GL and F, where F is a field, where F may be what? F is equal to Q, or F is equal to R, or F equal to C, or F is equal to ZP in particular case, or F is equal to F P raised to N, right? आपको F के लिए ये कोई भी दे सकते हैं, right? So here right now I am interesting here because we have discussed GL, NR, NR, NQ, NC, but now let us just discuss ZP. इससे पहले हमने कुछ डिस्कस किया था, कुछ ऐसा रिजल्ट था GL N ZP कोशेंट SL N ZP इट इज़ आइसोमॉर्फिक टू UP, ये एक रिजल्ट हमने डिस्कस किया था. बट आई वांट टू डिस्कस सम अदर थिंग अबाउट GL and ZP and SL and ZP. So let me give one notation. Let FP denotes the field having p elements, of course where p is prime, where p is prime, right? Okay. And we have already this one fact that F is any finite field, then cardinality of P is what? P to the power n, and here it is in particular case n is equal to 1. Okay. So now what I want to find, and let me write one more thing, ZP with addition modulo P and multiplication modulo P, and I will simply write it is ZP is a field having P elements and where P is prime. That is one thing. Okay. Yes. So now my question is this one: what is the cardinality of let FP is equal to ZP be the field having P elements where P is prime, then question is what is the GL and ZP. So what is the order of this GL and ZP? This is first question. Second question, what is order of SL and ZP? This is the second question. So I want to find out a solution of these two questions. Okay. So this is my next aim. Okay. So before going that, let us see how GL and ZP ये कैसे दिखेगा. So GL and ZP is what? It is collection of matrices Aij whose order is n by n, such that this Aij will be coming from ZP, and ZP is 0, 1, 2 up to p minus 1, and determinant of A, it is non-zero. So this is what GL and ZP. तो मतलब हमें क्या करना होगा, कि इसमें कितने एलिमेंट हैं, देन what we have to do, so you consider one element, say A, from GL and ZP, then it will look like A11, A12 and so on, A1n, A21, A22 and so on, A2n and so on. Let me write one more row, A31, A32 and so on, A3n and so on, an1, an2 and so on, ann. तो पहले तो मैं here what I have, all AIs belongs to ZP and ZP has P element. So here I have n cross n, that is n square elements, 1 2 3, like n square element. So this element has P choice, this element has P choice, this element has P choice, like that. How many elements I have? N square elements. So P into P into P into P, how many? N square times, that is P to the power n square. तो मैं n by n matrices whose entries are coming from ZP, ऐसे में मुझे कितने matrices मिलेंगे? P raised to n square matrices मिलेंगे, right? But among all these matrices, the determinant should be non-zero. तो ये जो P raised to n square element है, for example, if I consider n is equal to 2 and P is equal to 2, a small number, then it is P raised to n square is what? 2 raised to 2 square, that is 2 raised to 4. So it is 16. There are 16 matrices. तो ये 16 में से सबका determinant non-zero नहीं होगा, right? Some have determinant is 0. So those matrices whose determinant is 0 will not come in here. So what I have to do? I have to find only those matrices whose determinant is non-zero, right? Whose determinant is non-zero. Okay. तो ये कैसे find करेंगे? So let us just unfold this logic, how we count this. So okay, for that let us come back at school level. You forget about this discussion for a moment. Suppose I have a matrix, say A is a matrix, say A, B, C. Let me consider just a 3 by 3 matrix, A, B, C, D, E, F, G, H, I, some matrix. Then determinant of A is 0. ये कब 0 होता था? If all the rows of a determinant, I am considering row wise, if all the row of this matrix are 0, A 0 मतलब this like 0 0 0 D E F G H I, and suppose A is this, then determinant A is 0. So one way is this, all the elements are 0. और दूसरी चीज़ क्या थी? हमें सपोज ये फाइंड करने को बोले कि you just find out determinant, then what we are doing, we are trying to see that whether all the elements of row is 0 or not. If it is yes, then determinant is 0. The another technique is what? If it is not so, then you are just multiplying first row by 2 and you are adding in the third row, and if second and third row become first and second row becomes same equal, then also determinant is 0. Or if you multiply first row by some scalar and you multiply into the another row, and all the elements of that another row becomes 0, then also determinant is 0. तो मतलब what you are doing, कब 0 हो रहा था ऐसी हरकत करने से? But this is what, if you multiply some row by some scalar and if you add into some another row and it becomes 0, or it becomes the equal to the some other row, then it means what? That row, that two rows are linearly dependent, LD, linearly dependent. So determinant of A is 0, determinant of, so in general, let me write this result. A be any matrix, A be any matrix, then determinant of A equal to 0 if and only if rows of A are LD. if and only if rows of A are LD, linearly dependent. And similarly, determinant of A is non-zero if and only if rows of A are linearly independent, all the rows. Similarly happened for columns also, but I am right now interested in rows. So this is one fact. तो मुझे यहाँ पर okay, before going that, if I consider this matrix 3 by 3, so these rows are linearly independent or linearly dependent. It means what? You consider this row as a vector. You consider A, B, C, first row as a first vector of R3, second row D, E, F as a second vector of R3, third row as a third vector, that is G, H, I is a R3. So this is my x1, this is my x2, and this is my x3, vector of R3, right? See here A, B, C are coming from R. So R3 is what? It is R cross R cross R. This is R cross R cross R, R cross R cross R, right? So first row can be think as a vector in R3, and R is what? R is a field. R is a field, right? So here also you can think this first row of this matrix as a vector of Zp raised to n, Zp cross Z, because elements are coming from Zp. Here elements are coming from R. So first row is a vector in R raised to, here matrix is 3 by 3, so R raised to 3. So here first row can be think as a vector of the vector space Zp raised to n, Zp raised to n. See, to find out this I am using a little bit linear algebra. I hope you know the concept of linearly dependent vectors of linear algebra, and it is a very simple concept. So I will try to make it is simple. Okay, so ultimate what we will do, इसका डिटर्मिनेंट, ए का डिटर्मिनेंट नॉन जीरो होने के लिए क्या करना पड़ेगा मुझे? यू चूज द रोज. ये एलिमेंट चूज करने के बजाय नाउ आई विल चूज रो, सो दैट ऑल द रोज आर लीनियरली इंडिपेंडेंट. यदि ऑल रोज आर लीनियरली इंडिपेंडेंट, then my determinant of A will be non-zero. So now to find out how many elements in GL and ZP, that problem is converted into the fact that how many ways I can choose these rows, n rows, so that all the rows are linearly independent. So that is one milestone to counting the number of elements in GL and ZP. Okay, so I hope up to here it is clear. So now I will find, once again, now I will find how many ways I can choose rows of A so that all the rows are linearly independent. Yes. So where is my, yes. So now you consider this is say x1, this is say x1, a1, a2 up to an. So this is my x1. X1 is what? a11, a12 and so on, a1n. So it is what? It is a member of ZP. Yes, ZP. A11 is a member of ZP. So ZP cross ZP cross and so on ZP, it is n copies, right? So x1 is what? X1 is a member of this vector space. This is what? It is a vector space over ZP. It is a vector space over ZP. Now how many way I can choose x1? And keep in mind, I will choose every row so that all the rows becomes linearly independent, right? Okay, so how many way I can choose x1? So a11 has a11 coming from ZP, and ZP has p elements. Let me write here zp also. What is zp? Zp is 0, 1, 2 up to p minus 1. So this is my zp. So it has p elements. So a11 has p choice. Similarly a22 has p choice, and so on. a1n has p choice. So x11 has how many choice? P into p into p into how many times? It is n times, n copies. So it is p raised to n choice. So x1 has p raised to n choice. But among this choice, one choice is what? 0, 0, 0 and so on 0, because 0 is in ZP, a11 is 0, a12 is 0 and so on. So when all the elements are 0, in that case my x1 is linearly dependent, because 0 vector is always linearly dependent vector, right? And if I have all 0 elements, then determinant is obviously 0. So I am not interested in the matrix whose determinant is 0. I am interested in determinant should be non-zero. So among this p raised to n choice, you remove this one choice, that is p raised to n minus 1 choice. So matlab this x1 has how many choice? See, this is x1 and x1 has p raised to n minus 1 choice. This is my x2. So x2 has how many choice? So let us see. What is my x2? x2 is a11, a21, a22 up to a2n. So again it is an element of zp cross and so on cross zp. See, अब मेरे पास ये फर्स्ट रो चूज हो गई, दैट आई कैन चूज p रेज टू n माइनस 1. अब सेकंड रो चूज जब कर रहे हैं, देन आई हैव टू कीप इन माइंड दैट दिस टू रोज शुड बी लीनियरली इंडिपेंडेंट. तो इन दोनों को लीनियरली इंडिपेंडेंट रहना है तो क्या करना होगा? सो दिस रो, सेकंड रो should not be the scalar multiple of the first one, right? So that is what, if you consider say span, I hope you know what is span of vector. It is all possible linear combination of vectors. So you consider span of x1, right? Span of x1. So span of x1 is what? It is alpha times x1, where alpha belongs to, now my this is a vector space over zp, so alpha belongs to zp. तो ये span of x1 में क्या आएगा? All possible linear combination of vector x1, मतलब इस रो के हर एक स्केलर मल्टीपल आ जाएंगे, where alpha is from zp, right? Okay, now what are the choices for x2? x2 is a21, a22 and so on a2n. तो इसके लिए कितनी choices है? It is again element of zp cross zp. So a21 has p choice, this has p choice, this has p choice. So total are p raised to n choice. But among that the vector which is a scalar multiple of x1, वो जो x1 इसका जो मल्टीपल होगा वो कितने रहेंगे? मीन्स के इसमें कितने एलिमेंट है? सो कार्डिनलिटी ऑफ स्पान ऑफ x1, तो मैं अल्फा x1 इज फिक्स ना, x1 इज फिक्स. सो अल्फा कितनी तरह से मैं चूज कर सकता हूँ? अल्फा बिलोंग्स टू zp, सो इट हैज p चॉइस. सो स्पान ऑफ x1, द कार्डिनलिटी ऑफ स्पान ऑफ x1 इज व्हाट? इट इज p. तो ये x2 के लिए कितनी चॉइस हुई? टोटल p रेज टू n. उनमें से ये जो x2 है वो x1 का लीनियर कॉम्बिनेशन नहीं होना चाहिए, मीन्स p रेज टू n माइनस कार्डिनलिटी ऑफ स्पान ऑफ x1, राइट? इतने एलिमेंट निकाल दो, बट कार्डिनलिटी ऑफ स्पान ऑफ x1 इज व्हाट? p. सो इट इज p रेज टू n माइनस p, राइट? सो x2 हैज हाउ मेनी चॉइस? x2 has p raised to n minus p choice. Now you look at x3. So x2 has how many choice? So it is p raised to n minus cardinality of span of x1, and that is what? P raised to n minus p choice. Now you look at, this is x1, x2, now x3. x3 is what? A31, A32, A3n. So again it is element of ZP cross ZP cross and so on cross ZP. So it has how many choice? P into P into P. So it is P raised to n. तो जब मैं ये रो चूज करूं, अब ये दोनों का सिलेक्शन हो गया है. दिस रो कैन बी सिलेक्ट P raised to n minus 1 way. This row can be select P raised to n minus P way. Now what about this way? This row. So this row should be has total P raised to n choice, but out of this P raised to n choice, this should not be the scalar multiple of first one and it should not be the scalar multiple of the second one. But the scalar multiple of first one or scalar multiple of second one is what? It is just a span of vector x1 and x2. So it is what? It is alpha x1 plus beta x2, where alpha and beta belongs to ZP. So alpha has P choice and beta has P choice. So total is P square choice. So span of x1 x2, cardinality of span of x1 x2 is P square. So total x3 has P raised to n choice, but out of P raised to n you remove which are scalar multiple of x1 or x2, and that are P square. So it is P square. You remove from P square. So x3 can be choose P raised to n minus P square way, right? So x3 has how many choice? It is a P raised to n minus cardinality of span of x1 x2, and that is what P raised to n minus P square. So similarly the fourth one x4 will have how many choice? See, P raised to n, first row then P raised to 0, that is 1, second row then P raised to 1, third row then P square, fourth row then P raised to n minus P cube, so and so on. The last row, nth row, has, that is xn, it has P raised to n minus ith row then P raised to I minus 1. So nth row then P raised to n minus 1. तो अब एक साथ सबको सिलेक्ट करना है, तो then you just find out the product of all this, right? So this many way, this into this into this into this many way you can choose first, second, third up to nth row. In that case, no one row is the scalar multiple of its previous one, and as a result all the rows are linearly independent, and as a result determinant of A is non-zero. So you choose rows this way by this way and so on. So that many elements will be the elements of GL and ZP. So hence, so finally, so therefore order of GL and ZP is equal to P raised to n minus 1 P raised to n minus P into P raised to n minus P square and so on, P raised to n minus P raised to n minus 1. So this is the cardinality, very very important formula. So now our this problem is solved. Now it remains to solve this problem. So let us see how we can solve. Okay, before going that, let me give one example. You consider GL 3Z2. So what is the cardinality of this? What is the cardinality of this? Order of GL3Z2. So here n equal to 3 and P is equal to 2. So according to this formula, what we have? P, that is 2 raised to n, that is 3. 2 cube minus 1, 2 cube minus 2, 2 cube minus 2 square, and 2 cube minus 3 minus 1, that is 2. So up to P square only. So this will be what? 8 minus 1, 7, 8 minus 2, 6, and it is 8 minus 4, it is 4. So it is 42 into 4, it is 8 and 168. See, 168, this was the question asked in the NET examination. वहाँ पे ये सब डायरेक्ट नहीं बोला था कि you just find out the cardinality of GL3Z2. It is framed like this. Let some set is given. Let A be the set of 3 by 3 non-singular matrices whose entry is coming from a field having 2 elements. Then what is the cardinality of A? Then how many elements in A? So set of 3 by 3 non-singular matrices means 3 by 3 whose determinant is non-zero. 3 by 3 matrices whose determinant is non-zero and whose entry is coming from the field having 2 element and 2 is prime. So field having only 2 element is what it must be Z2, because any field having 2 element it must be the isomorphic to Z2 only, right? So they are just asking the cardinality of this set, but it is not given that it is GL3Z2. They just frame the question in this language what I said, right? But if you unfold this language, then it will turns out to be this set, and we have this ready-made formula. See, all this discussion is just to for understand, but whenever you have problem, then you just apply direct formula, right? So you need to just apply this formula here. And see, 168, between 1 to 200 there are two very important number. One is 60 and another is 168. These two are very important number. 60 किसका नंबर है? It is order of A5 और ये आपको ग्रुप 168 ऑर्डर का. This group is not simple. Sorry, this group is simple. Yes, this group is simple. 168 ऑर्डर का जो ग्रुप मिलेगा वो सिंपल, बट इट इज ऑर्डर ऑफ दिस GL3Z2. Sorry, it is not simple because see GL3Z2, so you consider SL3Z2. It is a normal subgroup of GL3Z2. So it is a normal sub, so it is a proper normal subgroup, right? So this group is not simple. Okay, fine. So now let us try to find out the order of SL and ZP. So now let me remove this thing. Let just me write this formula here. So we have order of GL and ZP is equal to P raised to n minus 1, P raised to n minus P, P raised to n minus P square, and so on, P raised to n minus P raised to n minus 1. So this is the formula. Okay. Now you consider a function f. You define f is a mapping from GL and ZP to UP. UP is what? What is UP? UP is nothing but ZP star. ZP star means non-zero element of ZP or units of ZP. When P is prime, so for example, suppose Z5. So Z5 is 0, 1, 2, 3 and 4. And P is prime. So 1, 2, 3 and 4 all have multiplicative inverse. Additive inverse to sabka hai because it is a group with respect to addition modulo 5. But with respect to multiplication modulo 5, only 1, 2, 3, 4 has inverse. 0 does not have any inverse, right? So whenever P is prime, then UP is what? ZP star, and it contains 1, 2, 3 up to P minus 1. then this UP with multiplication modulo P is a group. So this is a group and this is a group. Here operation is usual matrix multiplication, but whose entries is from ZP. So whenever you multiply two matrices of GL and ZP, you just multiply first row, first column, and at every multiplication, at every addition, you just use the multiplication modulo P. And I think in some previous lecture I illustrate one example how to multiply two matrices of GL2 Z2 or Z3. ये कुछ example दिया था. So I hope you know that, right? Okay, so now you define a mapping from here to here. F of A will be the element of GL and ZP is equal to just determinant of A. So whenever you find determinant, again you use the multiplication modulo P, whatever the number, so you reduce into the multiplication modulo P, then that element will be the element of UP. So this mapping makes sense, right? So then this map is what, when I prove this GL to ZP quotient SL to ZP is isomorphic to UP, at that time I have defined the same mapping, right? So then F is a homomorphism. I'm not going to say, proof is simple. F of AB, you consider AB, then it is determinant of AB, it is determinant of A, determinant of B, determinant of A is F of A, and determinant of B is F of B. So F is homomorphism, right? F is a homomorphism. First thing. Now F is onto. F is homomorphism, F is onto. Why it is onto? So you take set, let alpha belongs to UP. Now you consider matrix A, so that A11 entry is alpha, remaining diagonal entries are 1, and all the non-diagonal entries are 0, and it is a n by n matrix. Then what will be F of A? F of A is what? Determinant of n. Determinant of A is just product of diagonal entry, that is alpha. So for given alpha in UP, you have construct one element in GL and ZP, right, whose determinant, so that F of A is alpha, so F is onto. So that is what I have. F of GL and ZP is what? UP. Now kernel of F. Kernel of F will be what? It will be SL and ZP. Why? Because let me calculate here. Kernel of F is equal to what? A belongs to GL and ZP, such that F of A is equal to identity element of UP, and that is 1. So that is what? A belongs to GL and ZP, such that determinant of A is 1, and those elements from GL and ZP whose determinant is 1, it is what? It is SL and ZP. So kernel is this one. So by first homomorphism theorem, I think I am repeating the argument. Already I gave this argument in some previous lecture. By first homomorphism theorem, GL and ZP, that is G quotient kernel, but kernel is what? SL and ZP. It will be isomorphic to F of GL and ZP, and that is what? UP. It is isomorphic to this one, right? So order of SL and ZP divided by GL and ZP is equal to order of UP, and order of UP is what? It is phi p, where phi is what? Euler's phi function, and this is what? Order of GL and ZP divided by order of SL and ZP. I think you know, see G quotient H, then order of G quotient H is what? It is order of G upon order of H whenever G is finite group, right? Whenever G is finite group. So, and phi p is what? It is p minus 1. So therefore order of SL and ZP, you take this side, so it is order of GL and Zp divided by P minus 1. And order of GL and Zp is what? It is P raised to n minus 1, P raised to n minus P, and so on, P raised to n minus P raised to n minus 1 divided by P minus 1. Right? So order of SL and Zp is what? You just divide this quantity by P minus 1. So finally, what I have, order of SL and Zp is what? It is P raised to n minus 1, P raised to n minus P, P raised to n minus P square, and so on, P raised to n minus P raised to n minus 1 divide by P minus 1. So this is the another formula. Okay. Okay. See now one more point. तो यहाँ से मैं कोई एलिमेंट लूँगा GL and ZP में से. A belongs to GL and ZP. So implies determinant of A is what? It is non-zero. लेकिन जो भी determinant आएगा, determinant of A is non-zero and determinant of A will be what? So determinant of A will be, see, for example, you consider A belongs to GL. Just for example, you consider 2 by 2 matrices and ZP is say Z7. And for example, A is equal to, and Z7 is what? 0, 1, 2 up to 6. So you consider 3, 4, 5, 5 and 6, right? Or you consider say here 2, right? So 2, 3, 5, 6 all are elements of this. So what will be the determinant? Determinant is 18 minus 10, that is 8, right? So 8 is what? What do you mean by 8 in Z7? So 8 in Z7 is just modulo, so it is 1. और यहाँ पर ये भी आ सकता था किसी, let me consider here 5, so it is 30 minus 10, so it is 20, but 20 in Z modulo 7 is what? So it is 6, right? So ये 6 is what? 6 is element of Z7. पहले जो था 1 is the element of Z7. So whatever determinant of A belongs to GL and ZP, it will be the element of ZP. ZP का ही एलिमेंट होगा, राइट? नाउ नॉन जीरो कितने हैं वो पता चल गया. नाउ जिसका डिटरमिनेंट 1 कितने है, दैट इज दिस क्वांटिटी. सो नाउ वी कैन आस्क द सेम क्वेश्चन, हाउ मेनी matrices in GL and ZP whose determinant is 2. जिसका डिटरमिनेंट 1 है, दैट इज दिस नंबर. How many matrices whose determinant is 2? How many matrices whose determinant is 3? How many matrices whose determinant is 4? So in general, how many matrices in GL and ZP whose determinant is R, where R is what? R belongs to ZP. Sorry, R belongs to not ZP, UP. Because 0 तो नहीं होगा ना. 0 is not there. Right? Determinant 0 is not there in. So how many matrices in GL and ZP whose determinant is R and R belongs to UP? Actually it is what? It is in U7, and U7 is what? 1, 2 up to 6. 0 नहीं होगा, सॉरी, ए मैं यहाँ से ले रहा हूँ तो इसका डेफिनेटली डिटरमिनेंट इज नॉट 0. सो नॉट 0 मीन्स इट इज UP, राइट? ओके, फाइन. So let us try to give the, okay, let me first of all write that formula and then I will give just logic. How can we find that thing? So let R belongs to UP R belongs to UP, and UP is what? 1, 2, 3 up to P minus 1. Then you consider a set A belongs to GL and ZP such that determinant of A is equal to R. And let me give the set, this is SR. Then cardinality, I am writing here cardinality because now it may not be the group, वो group नहीं होगा for every R. If R equal to 1 then it is a subgroup, in fact it is a group, right? But for R is some other, then I can't say it is a group. So let me use the symbol cardinality. Cardinality of SR will be what? It will be same as cardinality of S1, and S1 मतलब determinant is 1. Determinant of 1 means it is a cardinality of SL and ZP, and it is what? It is this one, P raised to n minus 1, P raised to n minus P, and so on, P raised to n minus P raised to n minus 1 divided by P minus 1. तो सब की कार्डिनलिटी सेम रहेगी. मतलब लेट मी इलस्ट्रेट विथ वन एग्जांपल. मान लो कि फॉर एग्जांपल यू हैव GL 3Z5 है, GL 3Z5. सो देन यू हैव SL 3Z5. तो इसका कुछ ऑर्डर रहेगा, एंड यू कैन फाइंड आउट ऑर्डर विद द हेल्प ऑफ दिस फॉर्मूला. सो आई एम नॉट गोइंग टू फाइंड दैट ऑर्डर, बट यू कैन फाइंड, you just take P equal to 5 and N equal to 3 and you just calculate. So that will be a number. For example, this number is say this number is what I say it is K. It is K, right? Now you consider A belongs to GL. Okay, तो ये कोई भी, first of all, if I consider A belongs to GL 3Z5, then determinant of A is equal to what? It will be 1 or 2 or 3 or 4. इसी में से कोई होगा. तो 1 जिसका डिटरमिनेंट 1 है वो कितने एलिमेंट है? K. Now A belongs to GL 3Z5 such that determinant of A is 2. So if I consider this set is say it is S2, तो ये S2 में कितने एलिमेंट आएंगे? So that is also K. जितने एलिमेंट्स, जितने मैट्रिसेस का डिटरमिनेंट 1 है उतने ही मैट्रिसेस का डिटरमिनेंट 2 होगा, उतने ही मैट्रिसेस का डिटरमिनेंट 2 होगा, उतने ही मैट्रिसेस का डिटरमिनेंट 3 होगा, एंड उतने ही मैट्रिसेस का डिटरमिनेंट 4 होगा. सो सिमिलरली S3, here you have 3, then it is also K. S4, then it is also K, right? तो ये क्यों हो रहा है? Why it is so? So first of all you just keep this result in mind, and let me give the logic why it is happened so. See, हमने ये जो मैप बनाया था, logic is very simple. F is a mapping from GL and ZP to UP. तो यहाँ पर क्या था? This is my GL and ZP and this is UP. UP में कौन आ रहे हैं? 1, 2, 3, 4 up to P minus 1. और यहाँ पे तक जो कर्नल क्या थी? SL and ZP. ये मेरा है GL and ZP. तो ये जो पूरे एलिमेंट है इनका, और ये जो मेरा फंक्शन था, फंक्शन की डेफिनेशन कुछ ऐसी थी, f of a इज इक्वल टू डिटरमिनेंट ऑफ a. तो ये जो कर्नल है दैट मैप्स टू द आइडेंटिटी एलिमेंट्स. तो ये पूरे कहाँ पर मैप हो गए थे? 1 पे. करेक्ट. तो हमने एक रिजल्ट देखा था. इफ f इज अ मैपिंग फ्रॉम G to G bar, लेट मी राइट हियर. F is a mapping from G to G bar, and kernel, and this is homomorphism, and kernel of F, order of kernel of F is n, implies F is n to 1 map, n to 1 map. तो यहाँ कर्नल का ऑर्डर क्या था? मतलब कि जिसका डिटरमिनेंट 1 मिल रहा है उसका ऑर्डर क्या है? ये. एंड लेट मी से दिस नंबर इज K. तो ये k एलिमेंट्स है, इसमें कितने एलिमेंट है, k एलिमेंट, और k इज व्हाट, k इज बाय दिस फॉर्मूला। तो ये इतने एलिमेंट वन एलिमेंट को मैप हो रहे हैं। सो दैट एंड सपोज ऑर्डर ऑफ कर्नल ऑफ f, इट इज व्हाट, ऑर्डर ऑफ s l n z p एंड इट इज व्हाट, से इट इज k। सो ये मेरा जो f है वो क्या हो गया, f इज k to 1 मैप, इट इज k to 1 मैप। तो ये k एलिमेंट 1 को मैप हो रहे हैं, तो दूसरे k एलिमेंट का बंच मिलेगा। सो इट इज ऑल्सो कंटेन्स k एलिमेंट्स which maps to only one element, and that is 2, and this map is onto, so every element has pre-image, so this k element maps to 2, similarly another k elements maps to 3। तो ये जो एलिमेंट 2 को मैप हो रहे हैं उसका डिटर्मिनेंट 2 है, ये जितने एलिमेंट 3 को मैप हो रहे हैं उसका डिटर्मिनेंट 3 है। तो ये k एलिमेंट, बट k इज व्हाट, दैट इज कार्डिनलिटी ऑफ SL and ZP, and cardinality of SL and ZP is this one. So the number of matrices, total number of matrices in GL and ZP whose determinant is R, where R belongs to UP, is same as the cardinality of SL and ZP, and cardinality of SL and ZP can be evaluated by this formula, and it is just division by p minus 1 of the cardinality of GL and ZP, and cardinality of GL and ZP is given by this formula. So I think this is some nice information about GL and ZP and SL and ZP. Okay, so now we stop this lecture here, and in the next lecture we'll continue again in the homomorphism and isomorphism with some other interesting group. Okay, so thank you, we stop this lecture here, thank you.